Hi, good afternoon. One word of memory. One of the reasons that we're here today has to do with an old friend for many of us. When I was a graduate student, one of my co-students was a guy named Bob Brooks, and he had a career in the U.S. and then moved to here, moved to the Technion, and then had an abrupt heart attack and just died. And Ross Pinsky was cleaning out his office and found a copy of my book in his office. And, you know, which pile does it go into? You know, the throw-out pile or the non-throw-out pile? And Ross started to look at it and got interested in the subject. And that's part of the reason we're all here, actually. He decided to run this conference. So thank you, Ross, and we remember Bob Brooks. So the lecture I want to give today is, it will come to mixing times, but there's something very basic, and I call it the design problem, namely, we often work on somebody has a Markov chain and they're running it. How do you design Markov chains to do what you want? And that's what I'm going to talk about today. It's an extremely important area and not one that our community has done enough work on. I'm going to start with an easy example, and these are references, and I think I'm only going to do the first two, but I'd like to do the other ones, but it's only an hour. So here's how to generate an element from a group. And as you'll see, there are many nice consequences and problems. So suppose that G is a finite group. And you want to pick an element from G at random. And if you want to think about an example, of course, G could be the symmetric group, shuffling cards, or G could be the set of n by n matrices with entries mod P, invertible matrices, or any finite group. So here's an idea. Let H be a subgroup. Examples are coming in a second. And if you have a subgroup, you can choose coset representatives. X contained in G, coset representatives. And so all that means is that G is the disjoint union of X times H, where X is in H. So everything can be uniquely written as a coset representative times something in the group.
Outside H.
Sorry. X. Thank you. And now with this prescribed, so if you pick algorithm, pick X contained in X at random uniformly, H contained in H at random uniformly, then X times H, it's just obvious, is uniform in G. Just that everything is uniquely represented as X times H, and so that's. So let's do an example. Let's take G to be Sn, all permutations on n letters, and let's take H to be Sn minus 1, sitting in G as the set of all permutations such that pi of 1 is 1. So that's a subgroup, all permutations that fix 1. Now I have to choose coset representatives for H and G, and, well, one simple natural choice, so I just need some group elements which take 1 to 2, 1 to 3, 1 to, so the simplest maybe are, so choose X to be, the identity, 1, 1, I'll write the identity that way, 1, 2, 1, n. And so if you pick a coset representative, if you shuffle the bottom n minus 1 cards and then and then take the top card any place, that gets you a random permutation. Now you can use induction. So more generally, if you have G contains H, contains some other subgroup, contains H double prime, and keep on going down, contains H to the K, contains the identity. If you have a sequence of subgroups, you choose a sequence of coset representatives. You choose X and X1, X prime, X double prime, etc. And then H to the K is coset representatives for the identity in H to the K. And if you choose something random in here, something random in here, etc., then X times X prime times X double prime times H to the K, you choose something random in each one of these sets and multiply, that's the uniform distribution. So very obvious. And if you take in the symmetric group, Sn contains Sn minus 1 contains Sn minus 2. So Sn contains Sn minus 1 contains Sn minus 2 contains S2 contains the identity. And if you choose where Sn minus 2 is all permutations that fix 1 and 2, and you choose as coset representatives for Sn minus 2 in Sn, you choose the transpositions 2 with J. Then that's the algorithm that I told you about last time. That is, that's the algorithm. The standard way of choosing a random permutation is you have n memory registers, n cards. You pick an integer between 1 and n at random. That's this. And then you transpose that with 1. And then between 2 and n at random, transpose that with 2. And you keep going, right? And that's that algorithm, okay? If you, it's quite close to the surface. I noticed, so there, of course, there are lots of choices of coset representatives. For example, instead of transposing, you could take card J and put it on top, for example. Those are coset representatives, right? I noticed that any choice of coset representatives that I could think of, so any choice of n coset representatives, generate the full symmetric group. Can somebody prove that or give counterexample? That is, here, for example, these are the transpositions between 1 and n. If you take the group generated by these transpositions, that generates the group. Question, take any set of coset representatives for Sn minus 1 and Sn. I'll give you something to think about. Do they generate the group? Okay, there's no reason to do this only for finite groups. I'll do one more example, and this is a paper full of examples. Let me do the orthogonal group example, take On. And so how do you generate a random orthogonal matrix? This contains n minus 1, that's all matrices that fix the vector, the north pole, 1 and all zeros, for example. All matrices that fix any vector. And then that contains On minus 2 down to O2. Contains the identity, so that's a natural decreasing sequence of subgroups. And now I have to choose coset representatives for On minus 1 in On. Well, again, many ways to do that, but one simple natural way is the following. So I'm fixing the north pole, so I need matrices that take, anything to the north pole. Right? So one simple way is to use reflections. Take X to be the set of all reflections, the identity minus twice U transpose, where U transpose U is 1, a unit vector. So pick a vector at random on the unit sphere, and that's easy to do, where U is distributed, U is a vector of length n, as Z1 up to Z n divided by the square root of z1 squared plus and so on plus zn squared, where zi or I normal 0, 1. So if you pick a vector of normals, that's easy to do. Make it sit on the unit square. That's uniform on the unit sphere. Take that as those reflections. Those are coset representatives. And so This algorithm gives you a factorization of Haar measure, which is useful for a lot of reasons, but I won't go into that. That is, what do you do? Well, you would write I minus twice U, U transpose U, and then I n minus 1 minus twice U n minus 1 transpose U, etc., where this just means U1, all zeros, and then you put I minus twice U transpose in here. N minus 1 by n minus 1, you just keep going, okay? This algorithm is the best algorithm for generating Haar measure. It's called Stewart's algorithm. It's the fastest algorithm. It's the most numerically stable algorithm. It's the right algorithm. So those are two examples. If you want to think about something, take GLN over a finite field. I won't do it particularly here, but example, suppose as I had to in a cryptographic application, I needed a source, a lot of random invertible matrices, and so if you take GLN, FQ, take FP, F2, for example, those are n by n matrices. You have to think about what chain of subgroups to take. If you know a little group theory, one natural chain is to take these 1 star, 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 and all zeros in the first row contained in 1, all zeros, zero star, and then keep going. This is a reasonable chain of matrices. It's easy to choose coset representatives, and so it's easy to factor Haar measure. So that's what I mean by inventing algorithms for generation. Of course, this is perfect generation, and usually we can't do that, but when we can, it's a useful thing to be able to do. And so, okay, so that's all I'm going to tell you about this paper, but it's a useful thing. Okay, so usually we have things that don't have so much symmetry, and so that's the next topic, and let me try to learn from previous speakers and keep switching pens and see what happens. Okay, so the next topic I want to tell you about, and we'll fill the rest of the hour with it, is it's a unifying idea. It's called a hit-and-run algorithm. Where does Aaron Bonnet teach? Does he teach here at the Technion? You know Aaron Bonnet, he's in OR. B-O-N-E, what? Yeah, but was he here?
Not in this department.
No, but.
Yeah, it is.
So some people, he invented this, but somebody invented it 20 years before, but anyway. Okay, so here's the problem. Say I'll work on RD for the moment, on RD, and I'm given a probability density bigger than or equal to 0, integral of f of x dx is 1, say, or it doesn't have to be normalized particularly, but I'm given some density, and the problem is to pick samples from that. So that's a very general problem, and here's what the hit-and-run algorithm does. So it runs a Markov chain. You start someplace, so from little x, some little x. Put a unit ball around you. Okay, here we are. Here's x, here's the unit ball. Pick a point at random on that unit ball. I showed you how to do that before. Here's x. Pick y on b1 of x uniformly. Okay, just on the surface of the ball around you. That determines a line y through x, and then restrict f to that line. Restrict f to that line. It's then a function of one variable, right? It's a line. It's parameterized by t. Okay, so restrict f to L So this here's L. Restrict F to L, and sample from that. That, of course, won't be normalized. You have to normalize it, but OK, sample from that. So from this. Now, so you have to do a one-dimensional sample. Well, we actually know how to do one-dimensional samples. I'm sorry to tell you that. It's 2015. We know how to pick from probability densities. If you don't like that answer, take the line, discretize it into a million little pieces. That's a discrete measure. Just take f of x and pick from that. Okay, and then you can try to prove round-off errors. It's not bad at all. We know how to do this problem. Okay, in practice, and then just that sample from this to get x prime, and then keep going. That's one step of the Markov chain. Okay, this is a reversible Markov chain which has f as its stationary distribution, and let's try to think about it. Suppose that f was some multimodal horror. Now, I don't mean something that was invented to give analysts a nightmare, but there are mixtures of Gaussians. There are multimodal distributions. This algorithm has the possibility of going a long distance. You pick a direction. If you're in a bimodal thing, well, you have a chance of moving from one bump to another. Okay? So that's one of this algorithm can move long distances in one step. And so that's the hit and run algorithm. Where does the name come from? You hit a point on the surface of the ball, and then you run in that direction. I think that was the motivation. Okay, so now once you see this, then you could try to prove theorems about it. Okay, that's what we do in this conference. And there's been the first guy that did this rigorously was a guy named Smith, and he got total variation estimates under very, very mild assumptions. There are almost no assumptions in this. It works very, very generally. Lovas and Vempawa, and I won't give references, but if you look in this paper, I give plenty of them. Lovas and Vempawa showed that this converges. It's an easy case, but for log concave, f d cubed steps of this suffice. So that's. And if you want, this algorithm will surely work for things like mixtures of normals, and one could try to take examples and try to sharpen this theorem. Okay, now once you see this idea, and this idea, as I'll try to explain to you, is a very, very general picture, you can ask, why lines? Why the sphere? Why uniform? Why did we make these choices? If I had some other tessellation and wavy curves or something, couldn't it all be made to work there? And this can be made to work in great generality, and I'm going to do a little of that, and then I'm going to take some special cases and try to show you what it looks like in the special cases. This algorithm, which is a very clear, intuitive picture, unifies many, many different algorithms, so-called data augmentation and auxiliary variables algorithm, the Swedson-Wang algorithm, many, many algorithms in computational, whatever our subject is called, are contained in this as a special case. I'm going to do my generalizations in the special case of a finite set or a countable set. In the paper, we do it in repulsive generality. If you like that, you can do it yourself. If you like measure theory, I do too, but I'm not going to do that right now. So suppose that X is now, X is a finite or countable set, finite set. And pi of X is a probability on X. Examples are coming, but think of X as, all 52 factorial permutations, and pi of x is some non-uniform distribution on permutations. And the problem is to pick a lot of elements from pi of x. And so what I need to get started, I need some notion of lines. So I need Li of x, subsets of x, for I contained in some index set I. So I need a collection of subsets, and I think of those as lines, but they could be anything. Okay? And I will demand of these lines that they cover the space, the union of Li of x, I contained in x is all of x. So, but, you know, lines, maybe many, all lines. And I'll let I of x be the set of all I such that x is contained in Li. Okay, so number of the set of all these generalized lines that contain a point. So those are my lines. And then if I'm at x, I need to pick a line, right? That is through me. So so one ingredient, I need a set of lines. Second ingredient, I need omega sub x of I probability on I of x. So I'm at x. I look at all of the lines through me, and I have some way of picking them. Not uniform, not anything, just some measure. Okay, you know, say positive. I mean, and so that's pretty general. And then I need a way of moving on the line, and it's going to be the analog of this restriction. But because I'm not uniform on the line, the third thing I need, and I only need three things to make this work. The third thing I need is I need, so I'm on the ith line. I need ki of xy. A Markov chain on Li, the ith line, with pi of x times wx of I as stationary. So this might be uniform, but it might not be. And that's the one idea in here, is this is the way you have to adjust for the fact that if you don't choose the lines at random. So again, there are many ways of doing that. It might be it's a finite set. You could just pick uniformly from this, you know, normalize this to be a measure, pick from that measure. So right, this is y. I mean, it's a right. I need a way of moving around on this line this way. And then the algorithm is just the following. Let putting these ingredients together, define a Markov chain k of xy to be, I'm at x in this space, to be the sum over I of w sub x of I times k sub I of xy. So pick a line and then move on that line. That's the analog of hit and run. And so I don't know what to call it. I'll call it a fact, a proposition, lemma, something trivial. This has k has pi as stationary. And if ki is reversible with respect to that measure, then this is reversible with respect to pi. But let's just check that proof. The sum over x of pi of x, k of xy, it's supposed to be pi of y coming out the other side. Well, it's just the sum over x of pi of x, the sum over I of w I x ki of x y. here's this measure. This is the sum in I of the sum in x of pi of x, w I of x, k I of xy. I didn't do anything, but now this kernel has this as its stationary distribution. This is the sum in I of w sub I of y times pi of y. Just using stationarity, take this pi out. This is a probability. So this is pi of y. Right, so it's trivial. As you'll see, it includes many, many special cases that are not the first thing you would think of. I'll just put it that way. So, of course, if you just want something to think about, a picture of this, it is very general. How should you think about this? Well, often the size of I of x doesn't depend on x. Well, this is k. And then you could just use, and so then use w sub x of I equals 1 over k. So pick a line at random if you like. And an example of that, suppose you're in 2 dimensions on a finite grid in 2 dimensions. These are my lines, and then I have f of xy, pi of xy. Is my measure, and so if I'm at a point xy, there are 2 lines that go through me. I pick one of them at random, say this one, and then I sample from pi restricted to that line. That's called the Gibbs sampler or Glauber dynamics. It's a very, very familiar idea, so that's a very, very special case of this algorithm. But as you'll see in a second, there are more interesting cases. There's nothing wrong with this case. It's maybe one of the most widely used tools in scientific computation. So, okay, I'm going to say a variant which is called auxiliary variables. So, example, auxiliary variables. So now, everything I've said up to now, so hit and run has a very clear geometric interpretation, right? I'm at a point, I pick from the lines through me, and then I run in that direction. That geometric interpretation is lost in the many recodings of this algorithm, but it's useful to remember because it is basically a very geometric. So auxiliary variables goes this way. We're given some probability density, say f of x on some space or other. And now I'm going to go backwards. Let I be an arbitrary index set. It could be continuous, I don't know, but it'd be this. You'll see examples. Be any index set. Let w sub x of I dot I be a probability on I. So at x, I've got to choose an index. And if this is continuous, then this will be a density with respect to some measure. But OK, so I just have some way of choosing an element of I. These two ingredients, a measure on X and a kernel on going from X to I, they define let me call it f of xi on x cross I by f of xi is equal to, well, f of x times omega sub x of I. It's just that, you know, if I have these ingredients, that's a probability distribution on that product space. And so there's a conditional distribution. And so f of x given I, the conditional distribution of x given that you're at I, just by the usual, you know, definition of conditional probability. And so and now I need a kernel k of I of x y with f of x given I as stationary. And again, examples are coming in 1 second. So, and then I can put things together in just exactly the same way. With these ingredients, I define a kernel on the whole space k of xy as the sum, I'm at x, of w sub xi times k sub I of xy. And this here, I'm summed over I, or I'd integrate over I. So this is the same algorithm, it's just said in slightly different language. Here the lines, if you want to think about lines, the lines Li is the set of all y such that w of xi, no, w of yi is bigger than 0. I think that's right, but you don't need this in order to understand this. So this algorithm is called the auxiliary variables algorithm. It was introduced as an abstraction of the Swedson-Wang algorithm by Edwards and Sokal in a very, very nice paper. So now it's the rest of the talk is examples, and so it all seems trivial, but it's not so trivial when you get down to work. Okay, so let me give you an example of now, what example did I want to give you? And then, it's hard to read them without my glasses, but okay, I can see enough, and it's in here too. So just to not ramble off into infinite space. So here's an example. Take X to be a finite set, like permutations, and let T from X into R to the D be any old function, any function, and define a probability, I'll call it pi sub beta of X, as a normalizing constant, z inverse of beta, which we usually never know, times e to the beta dot t of x. Here, beta is contained in Rd. So for fixed beta, this defines a probability distribution on x. And many, many problems can be put in this guise. I will specialize in a second. And the problem is to sample from this pi. Okay, so I'm going to follow auxiliary variables, and I'm going to let I, my index set, be equal to 0, infinity, to the D. That is a set. And now I need a way of moving into I from X. So let W sub X of I, I'll try to put a, so I've got to choose a real D tuple. W sub X of I is uniform on the set of all I such that I sub j, the jth component, is less than or equal to e to the beta j t j of x. X is fixed here. Beta j, this is the jth component of this vector t of x. This is a certain number. And so this is a compact cube, rectangle. Right? This is a compact rectangle. It's trivial to generate from the uniform distribution. It's just a rectangle. Just pick the coordinates at random from the uniform distribution. It's trivial. So that's my way of moving around. How do I move back? Let k sub I, how do I move back? Well, xy be equal to the uniform probability on the set of all y such that I sub j is less than or equal to e to the beta j t j of x. So, sorry, y here, y. So there's some set of y's, at least it includes x. There's some set of y's which you have to figure out what this is, and I'll do some examples. There's some set of y's which satisfy this inequality. You have to be able to pick at random uniformly from that set of y's. That gives you a two-step algorithm that is from x, pick I from this rectangle, and then pick a y uniformly in here. And that satisfies everything that we're talking about. And so let me now specialize to a real example. But this is the Swedson-Wang algorithm, essentially, but said in this generality. Okay, so real example, so say x is Sn, n is 52 if you like, and let pi sub beta of sigma, sigma's a permutation now, be equal to a normalizing constant, which we don't know, is the inverse of beta. Beta is a real parameter, times e to the beta times the sum from I equals 1 up to n of sigma I. I'll take it centered at the identity, minus I squared. So if I write that down, that puts a probability distribution on permutations. There it is. Okay.
Now our D is 1 now.
Yeah, D is 1. Right here, D is 1. And this is called Mallow's model. Through Spearman's row. But so I could replace this by any metric, the distance to the identity, but I'm taking, this is a very widely used one. So of course if beta is 0, this is the uniform distribution on permutations. When beta, let me put a minus there, just, okay. When beta, if beta is a large positive number, this measure concentrates around the identity, right? It gets more and more peaked around the identity. And this is a measure that's used by people who work with non-uniform distributions on permutations. And you might very well, in testing algorithms for estimating parameters, often this identity might be replaced by a location parameter and some unknown fixed permutation, and you have a sample and you want to try to estimate this and beta. That's a standard statistical task. Anyway, problem sample from this measure. Now, the knee-jerk reaction, my knee-jerk reaction is, okay, I'll try the Metropolis algorithm. I'm at some sigma, make a random transposition. If that increases the probability, go there. But I want to look at what auxiliary variables does so that you can see that these steps can all be carried out. Okay, so the first thing to do is to rewrite that. This is, maybe this changes a little bit, z inverse of beta. Let me square this out. E to the sum, there's it's now plus beta times I times sigma I. The sum of I squared and the sum of sigma I squared, that's a constant, right? So you can just absorb that into the normalizing constant. So this is the same measure with perhaps a change of normalizing constant. And so this has that form, right? It's an exponential model with n TIs, right? So what do I do? So from some sigma, I'm at some sigma, choose what do I choose actually? Here I'm going to choose I1 up to IN, maybe I should call them something else. Let me call these U1 up to UN in the set of all U such that Uj is less than or equal to e to the beta beta times j times sigma j. Okay, that's just, this is a finite set. And then I have to, from U, this choice of U, choose, I call it sigma prime, second permutation in the set of all sigma prime such that Uj is less than or equal to e to the beta j sigma prime j. Now, so I have to choose a permutation which satisfies these constraints. That is to say, I need sigma prime of j bigger than, let me take logs of both sides, bigger than or equal to, let me take logs of both sides and then divide. So bigger than or equal to log of u j divided by beta times j. Beta is fixed in this, and I'll call this bj. So I'm given some numbers bj, and I have to choose a permutation so that coordinate-wise, this has to hold for all j. Coordinate-wise, my permutation is bigger than or equal to some numbers. This is trivial to do once you get your head around that it's, you need to do it. It's easy to do this. That is, take j as 1. So I need to, I'll say it this way, look at the set of all k such that bk is bigger than or equal to 1. There'll always be at least one element in this set. Put 1 in that, okay? That'll be sigma of 1. So this is size bigger than or equal to 1. Pick an element in here, in this set here uniformly, and put 1 in it. And then just keep going. Look at the set of all k such that b of k is bigger than or equal to 2. There'll always be at least 2 things in this set. Now, one will probably occupy, but there might be more, there often are more. One will occupy one of those places, put 2 in one of the remaining places, and just keep going. So put 2 in and keep going. So this is an easy task to do. And now that you understand this idea of moving far, you can see these are very violent algorithms. It's nothing like random transpositions. Given a permutation sigma, you know, I can go very, very far away in this sampling. If you want a problem, there are 2 interesting problems. Understanding the behavior of the metropolis algorithm in this problem based on random transpositions, completely open. Nobody has thought about it. Okay, that's a problem, but I don't think it's a very good algorithm. I have tried this one out a fair amount, and it works pretty well, but try to prove something about this algorithm. That's a reasonable problem. I'll give you some examples of problems like this where I can prove things, but this is a kind of natural extension, and try to get bounds on its running time.
How does beta come into play here?
Beta's a parameter, and so if it's close to 0, it's easy because it's sort of, you know, uniform and, you know, high temperature, and if beta's big, the sets are littler. But all of that's part of the question, but, you know, try to understand it. But, oh, it doesn't seem to matter. That is, I tried it with a variety of betas. It really goes all over the place, just as you might hope it does, you know. So, so there are many special instances of, this is a very general setup. There are many special instances. I just chose one. Now tell me what time it is. 10:02, okay. I want to do one more class of examples, and again, there are many, many problems, but I have proved some theorems. So the last example is I call computational polya theory. And it sounds easy. It is easy, but it's easier if you have a beautiful black pen. Watch this now. Okay. So the setup is, in case you're asleep or lost, new talk starting. Okay. X is a finite set. Yes, of course, finite set. G is a group acting on X. Okay, so given X, I have some way of moving around. The action of a group on a set splits the set into orbits. So X is equal to O1 union O2 union OK. These are the orbits of the group acting. And the problem is to choose an orbit at random. Now, of course, put that way, pick an integer between 1 and k at random, but it's not quite that simple. You don't know k, and you don't have a description of the orbits usually. But that's the problem. So just to give some legs to this problem, this is the problem of choosing unlabeled objects. So e.g., suppose that x is equal to all unlabeled trees. On all labeled labeled trees on n vertices. So, okay, we know how many labeled trees there are. There are n to the n minus 2. The size of x is n to the n minus 2. And there's a very nice way of you know, these are labeled by proofer codes, and there's a very nice, very simple way of choosing an element to that. But now suppose you want to, and now let the symmetric group act, let the SN acts on the labels. And so the orbits are unlabeled trees. So for example, when n is 5, there are 3 unlabeled trees on 5 vertices. There's a path. There's that thing. Well, that's just that thing, and then there's a star. Those are the. So, you know, n is 100. Choose an unlabeled tree at random. That's a special case of this problem. Okay. So here's the Burnside process. This is a Mark Jerram. Other work with Leslie and Goldberg. He called it the Burnside process. And it goes like this. It's a Markov chain on X, from X. Choose G uniformly in G sub X, which is the set of all G such that G fixes, X is fixed by G. So given an X, there's a subgroup of elements that fix X, and that's a set, and you have to be able to choose from that set. And then from G, choose Y contained in X sub G, which is equal to the set of all Y such that Y to the G is Y. So from X, you choose a group element that fixes it. From that group element, you choose among its fixed points at random. That's a two-step process. The chain, and it is a special case of these constructions, that's K of XY, the chance of going from X to Y in one step. And so, easy fact, this has stationary distribution pi of x, which is proportional to the 1 over the orbit. We know the normalizing constant, the size of the orbit of x. So if you run this Markov chain and then just report the orbit that you're in, that will be uniform on the set of orbits. And these are easy things to verify. So let me give you an example, simple example. But again, there's lots of groups and lots of sets and that they act on, and any one of them are research problems. But here's one where we did the work. So I'll do in the simplest case example. Let me take X to be the set of binary n tuples, C2 to the n, set of binary n tuples. And let me take G to be Sn, acting by permuting n tuples. So the orbits are, you know, O0 union O1 union On, where OI is the set of all binary n tuples which have I1s. Those are what the orbits are. Okay. And so I'm really wanting to choose an integer between 0 and n at random, but I'm not putting it that way. And so what's the algorithm? You know, from X, I'm at some X. What are the set of all permutations that fix X? Well, I can permute all the 1s, and I can permute all the 0s. So it's Sk cross Sn minus k, right? That's all. You know, so choose, I'll call it G, contained in Sk cross Sn minus k, where the number of 1s in X is k, you know, the right size. So that's very easy to do. And now, how do I choose something which is fixed by a group element? Well, just from G, if G fixes it, G squared fixes it, G cubed, it has to be constant on the cycles of the permutation. From G, factor into cycles. And just color them at random. See, color them 0, 1 uniformly. Flip a coin. So just that gets you a new binary n tuple, right? And that's this algorithm. So you know, that's the most special case. And then you can ask about the running time of this algorithm. And I did prove, and Aldous proved, two different theorems. But I proved that the total variation distance of this after L steps, say, started at all zeros, minus its stationary distribution, is less than or equal to 1 minus 1 over pi to the L. So it's very fast. Now, there's nothing special about a two-element set. You could take k colors, and then the group acts, and then the invariants, the orbits, are, you know, how many indices, how many places, you know, have color 1, how many places have color 2, etc. And this distribution over vectors that sum to n in k colors is called the Bose-Einstein distribution. And Aldous proved that the distance with k colors, the distance after L steps to stationarity, this pi is 3.1 point, yeah, right, is less than or equal to n times 1 minus 1 over k to the L. And his argument is much better than mine if k is large, but if k is 2, it gets the wrong answer, and this gets a better answer. So if you look at these papers, and all of that is in my paper with Hans Andersen, if you look at these papers, you'll see the techniques are quite different. These are not local algorithms, so the usual kinds of nearest neighbor things that we use aren't good ways of proving theorems in this case. He did prove this by coupling, and I proved this by a kind of fancy version of a Dublin type argument, Harris recurrence type argument. Okay, the last thing to say is these other papers are filled with other examples. This is how to generate random contingency tables, or for logistic regression. There are many, many problems in which one wants to sample from unusual distributions on finite sets, and this is what it says. How do you sample from a manifold? And these are all filled with examples. I do think it's worth understanding that inventing algorithms to do sampling is something we can do, that we should be good at, and we should be doing more of. Not just, you know, taking some problem that somebody, you know, make a better one. If you can add one move to an algorithm, it can really speed it up by a lot. So that's my second lecture.